Welcome to lecture number 2 of structural dynamics. In this lecture, we start off our learning of the subject matter by looking at the very fundamentals of the problem. So we will, um, you know, find out how to formulate equations of motion of a dynamic structure, of a structure that has been dynamically excited, and what are the different solution methods that we use to solve these dynamic equations. So, the first concept that I would like you guys to consider is the degree of freedom. Now, I assume that all of you are familiar with the basic structural analysis concepts. So therefore, this concept is just presented as a brush up of your understanding of structural analysis, because I assume that you are all very familiar with the structural analysis concepts. There are different ways to define a degree of freedom, and my preferred way to define a degree of freedom is to define it as follows. The degree of freedom of any structural element is the minimum number of translational and rotational movements of the structure that will completely describe the deformed shape of the element. You know, so let's consider a beam element that is shown in right here. The beam element consists of two nodes, node 1 and node 2. Each node can either move up or down, and each node can also rotate. So the total number of minimum translational and rotational movements that are required to completely define the deformed shape of the element is, in this case, is 4. Now, on the right side of the figure, you know, is shows as to how these four translational and rotational degrees of freedom are related to the deformed shape of the continuum, and this is by using shape functions. So there are four shape functions, n1 and 3, which relate the deformed shape of the continuum to the movement of the left node and the movement of the right node. And then is n2 and n4, which relate the shape of the continuum to the movement of the rotation of the left node and the rotation of the right node. Of course, any general deformed shape is a combination of all four of these shape functions and degrees of freedom. Now, as we will learn later, the degrees of freedom that are required to describe the stiffness properties of the structure is typically more than the degrees of freedom that are required to calculate the inertial properties of the structure. So, look at this frame. The degrees of freedom, and we assume that the axial stiffness of the members of this frame is infinite. So there is no axial stretching going on. If we assume that, then the deformation, the lateral deformation at the top of the frame on the left side and the right side are both equal to u, right? And then there is the rotation of node number 1 and rotation of node number 2 that we are concerned about. So the degrees of freedom that are required to describe the stiffness properties of this structure is 3. On the other hand, the mass can only, and we are assuming that the mass is lumped, as we will learn later, we are assuming that the mass is lumped at the top floor of the, at the roof level of the frame. And so the mass can only move horizontally, and because we are not assuming any rotational excitation of the supports, and therefore there is only one way in which the mass can move, and therefore the degree of freedom that is required to represent the inertial property of this frame element is 1. So here is an example of a typical scenario where more degrees of freedom are required to describe the stiffness properties of the structure as compared to the inertial properties. Next, let's look at a number of idealized systems that can be categorized as single degree of freedom systems. For ready reference, let's label all of these figures, and let's start by looking at the pendulum that is shown in figure 1. Now the pendulum consists of a mass m that is connected to the support through a rigid bar. The bar is rigid flexurally as well as axially, which means that the bar will not stretch and the bar will not bend. The question at hand is, how many degrees of freedom do we need to know for us to completely define the deformed configuration of this pendulum? And it can be easily seen that all we need to know is the position of one of the points on the rigid bar with respect to the vertical as a function of time t to define the deformed shape of the pendulum. Similarly, consider the rigid bar that is shown in figure 2. The rigid bar is connected to the support through a frictionless hinge, is supported by a spring at B, and a dashpot is connected to the rigid bar at C. So again, all I need to know is the position of only one of the points on this rigid bar with respect to the undeformed shape of the bar to completely define the deformed configuration of this beam. Again, in figure 3, there is a rigid bar, but this rigid bar has a uniform mass m throughout its length. The rigid bar is connected to the hinge at O, and all I need to know again is the position of one of the points on the rigid bar as a function of time t to completely describe the deformed configuration of this bar also. In figure 4, there is an assembly of two bars, and the two bars are connected to each other via hinge at the center, and so this is a determinate system. We can calculate all of the reactions in the springs and the supports using equations of equilibrium. So the question again is, how many degrees of freedom do we need to have to completely describe the deformed shape of this bar? And we can easily see that if I'm trying to draw a triangle here with a hinge over here, all I need to know is the position of one of the points, either at the hinge or along one of the beams as a function of time t on these bars. So, all of these the rigid bar systems that we have looked at all of them are single degree of freedom systems. In figure 5, we presents a problem that is much more familiar or relevant to us civil engineers. And, it's a single story frame with an infinitely rigid beam element. So, you know, all we need to know for this single story frame is we need to know the magnitude of delta at any time instant t to completely describe the deformed shape of the structure. So the question that arises naturally is, what if we have beams that are not flexurally rigid? Again, we can see that since the mass can move only in the horizontal direction, we are only interested in this direction to describe the inertial properties of the frame element of the frame. And so whereas, as far as the stiffness is of the frame is concerned, we have to have two rotational components and one translational component to completely describe the stiffness of this frame element. This, as far as inertial properties are concerned, we only need to know the magnitude of delta as a function of time t. And so this um, structural element is also a single degree of freedom system. Next, let's take a closer look at the single story frame that we have been looking at in the previous few slides. Let's um, calculate these degrees of freedom that are required to describe the stiffness properties of this frame, as well as the degrees of freedom that is required to describe the inertial properties of this frame. Now, if I'm not making any assumptions, and let me label the nodes. If I'm not making any assumptions, then my node 1 can move in the horizontal direction. My node 1 can also move in the vertical direction. My node 1 can rotate. Similarly, my node 2 can move in the horizontal direction, the vertical direction, and it can also rotate. So the total number of degrees of freedom that are possible, or that are the minimum number of degrees of freedom that is required to describe the deformed shape of the frame element, is 4, 5, and 6. But this is more often, than not, this is the simplified. And there are a number of simplifications that we introduce into this problem to study the dynamic properties of frame elements. The first assumption that we make is all frame elements are axially rigid. Now, how reasonable is this assumption? I would say pretty reasonable, because the axial stiffness of these frame elements is of many orders of magnitude higher than the flexural stiffness. So we do not lose much of an accuracy by ignoring the axial stretchability of all of these frame elements. Um, so once we have assumed this, the degrees of freedom of the frame elements reduce, because if all of my frame elements are instretchable, then my degree of freedom 2 and 5 is equal to 0, and my degree of freedom 1 is equal to 4. The only two other degrees of freedom that are there and that remain are degrees of freedom 3 and 6. So with this assumption, my degree of freedom to describe my frame element reduces from 6 to 3. Those three degrees of freedom are the rotation at node 2, the rotation at node 1, and the horizontal motion of the roof of this frame. Another assumption that is typically introduced into these problems is that mass, whereas um, actually the mass is distributed throughout the length of the column and beam elements, we assume that mass of the column elements is half of it is lumped at the base of these elements, and the other half is lumped at the top of these column elements. Typically, beams carry all the floor load, and therefore it is assumed that beams have the mass distributed along the length of the beam element. Now, since we are only studying the lateral deformations in the frames, the mass of the columns at the roof level and the mass of the beam, all of them are lumped at the center of the frame, and this will give us equivalent results because uh, all of the mass is um, sort of moving back and forth at the roof of the frame element. Again, how reasonable is this assumption? Well, um, the mass associated with the column elements is typically many times less than the mass of associated with the horizontal members such as beams, because beams are supporting all of the slabs, and the self weight of the columns or the self mass of the columns is the only source of mass for the columns. Now, columns can have considerable sizes, but typically this is not the case, and therefore this is a reasonable assumption. Next, let's look at a frame in three dimensions. And let me label these nodes for ready reference. 4, 5, 6, 7, and 8. There should be a node here. 9, 10, 11, and 12. And the question is, what is the minimum number of degrees of freedom that are required to describe the deformed shape of this frame? Now, to answer this question, let's look at one of the nodes closely and um, think about how many ways in a particular node can move or rotate. Now, if I look at my node number 8, this node can move in the x direction, can move in the y direction, will move in the vertical direction. It can also rotate about my x axis, about my y axis, and about my z axis. So there is a total of 6 degrees of uh, there is a total of 6 degrees of freedom associated with each one of these nodes. So if I am considering a frame that is fixed at the bottom, the total number of degrees of freedom associated with the definition of the stiffness properties of the frame is simply 6 times the number of free nodes, which is 8, and therefore my degrees of freedom for this frame is 48. Now, we do typically make assumptions when we are analyzing three-dimensional frames. And the assumption again is that the horizontal frame elements, which is beams and slabs now, are not extensible. They are axially rigid and in plane rigid. This reduces the number of degrees of freedom by more than half, and we analyze the simplified structure. On the right side, you see a triad, and this triad actually is a blow up of one of the nodes, and this shows all of the possible degrees of freedom associated with each one of these nodes in 3 dimensions. Next, let's start looking at actual problems that can be categorized as single degree of freedom systems. On your left, a structure is shown which is basically a pergola, and the problem at hand is to calculate the dynamic response of this structure due to lateral loading in this direction. And we can see that it can be very easily done by making a certain set of assumptions. The first assumption is that the slab is infinitely rigid, which basically means that when the columns are connected to the slab, right, at these 2 points, the deformations of these 2 points is related to each other. It, so the slab will neither stretch in the membrane direction nor will distort in the membrane direction. Now this, because of this assumption, what we can assume is that we can take we can take half of the slab and attribute mass of half of the slab to this column, and half of the mass is attributed to this column, right? Next, we assume that the columns are massless. How reasonable is this assumption? Well, the columns are hollow points, and therefore their mass is many times less than the mass of the slab at the top. And therefore, this is actually a reasonable assumption. The third assumption that we make is that the columns are linear during the dynamic response of the structure. Now, this is a reasonable assumption because we are mostly designing structures to remain linear during earthquakes. But if you feel that the nonlinear dynamic response of this structure is desired, then basically this is not a reasonable assumption, and we need to then resort to special methods to solve this system. Now, each one of these columns, this column and that column, can be idealized as a single degree of freedom system consisting of a pole that has a mass m at the top, and the mass can only move in the lateral direction because the pole is also assumed to be axially stiff. So it can move either in this direction or in that direction. And since this is just a single, we just need a single translational degree of freedom to completely describe the system. Um, this whole structure can be analyzed for dynamic effects using a single degree of freedom system. Next, consider this elevated water tank. The water is stored at the top of the tank, and the pedestal of the tank is a hollow concrete structural element. Now, when the water tank is full, most of the weight of the structure is due to the water that is stored at the top of the tank. Whereas this element, the pedestal, also has mass, but since it is probably, I would be designing this, it is probably hollow. This, the mass of this pedestal is many times less as compared to the weight that it is supporting. Also, we assume that the water is completely full in the tank, and therefore there is no sloshing of water inside the tank. We've already explained as to how reasonable the assumption of massless column is. Again, we are considering the linear response of the structure subjected to lateral loading. And again, this structure can be idealized as a single degree of freedom structure because all you need to know is your lateral dis- displacement of the mass in, and since the column is assumed to be axially inextensible, there will be no vertical movement of the mass, right? So this is also an example of a single degree of freedom structure that can be analyzed easily using. Now, in classical dynamics, the single degree of freedom system is idealized by the mass trolley system that is shown on this slide. The mass is supported on wheels which are moving back and forth on a frictionless free surface. The mass is attached to the support through a spring of a dashboard of damping value C. The force is applied to the mass towards the right or left, and the mass can only move in the horizontal direction. Now, the free body diagram of the mass is shown adjacent to this mass trolley system, and this is basically resisting the weight of the mass. So, this is basically the reaction of the wheels. This is the applied load. The damping acts in the direction opposite to the direction of the velocity, and then this is the force associated with the spring. In addition to all of the above forces, from Newton's second law, we know that if there is an acceleration, there will be an inertial force in the mass, and this inertial force is actually um, what is shown here in this figure on the right. Now, um, at the bottom of the slide, we have an equation of motion. And this equation of motion is basically the equation of motion of a single degree of freedom system when there is no damping in the system and when the system is vibrating freely. so there is no external force applied on this system. And we can solve this linear differential equation and get they get the displacement of the mass as a function of time. If we do that, we'll get a plot that looks like this. And note that the oscillations of the resulting system never die down. We will discuss this later, but this is because we have assumed that there is no damping associated with the system, damping being the energy wasted during oscillation of a dynamically excited system. Next, let's take a look at the different components of the single degree of freedom system that we have talked about in this lecture. And this slide starts to introduce the concept of stiffness. Um, Consider the frame, single story frame that is shown in figure. The single story frame is being pushed towards the right at the top, and as the single story frame is being pushed, the force deformation plot is shown in figure C. Now, initially, when there is no lateral deformation, there is no force being applied or resisted at the top of the frame. As the frame is pushed towards the right, there will be a linear increase in force with the increase in lateral deformation until there will be a point where this departure from linear deformation will be observed. Now, if at this point the direction of lateral loading of the frame is reversed, it will not follow the initial loading curve. Instead, it will unload by a new path starting at point A and hitting the zero force response at point B. If the loading is now continued in the negative direction, this frame will continue to resist load, and the resulting force displacement plot will be shown will be shown by the branch BC on this plot. If at this stage the loading is now reversed, the unloading branch or the reloading branch will be line will be this curve through point D again to point A. So the point to note is that once we enter the nonlinear range, we not only need to know the current deformation in the system, but we also need to know uh, about the history of loading and unloading of the system. And but within the linear range, it doesn't matter because we will be loading and unloading on the same line. Now, most of the problems or all of the problems that we are gonna talk about in this course are uh, within the linear range, and therefore we are not bothered about the nonlinear range of the stiffness. So, but since many of you would not have a clear concept of what stiffness is, within the linear range, stiffness is nothing but force required to cause unit deformation. So, if I have a lateral deformation value of u is equal to 1, right? To get my ink here, u is equal to 1. What I'll do is I'll go and intercept this force deformation curve and simply get the value of force at this u is equal to 1. So my k value would simply be fs1 over u is equal to 1, which is equal to fs1. And similarly, but I can utilize any other point on this linear line. I can have a u value which is less than 1, let's say 0.5u, and then I will have fs zero point 0.5, and what again I can calculate k is fs zero point 0.5 over u in zero point 0.5. So, but this value of k will be equal to the other value of k because the line is linear. The plot that you see on your right is basically shows the nonlinear response of the system, and um, it becomes evident that we not only need to know our current position on this plot, but we also need to know as to what the history of loading of this structure is. Let's take a look at stiffness of frame elements. Since we will be formulating and considering axial stiffness of the frame element separately, eh, on this slide we will consider only stiffnesses that are related to flexural stiffness of the frame elements. Now the figure on the top shows generalized displaced state of the frame elements. This generalized displaced state of the frame elements is completely described by four degrees of freedom, which is UA, theta A, UB, and theta B. And there are two fundamental types of um, stiffnesses associated with the frame element. The first type of stiffness associated with the frame element is called the rotational stiffness of the frame element. And the second type of the stiffness is called the shear um, flexural stiffness. And basically, let's look at the rotational stiffness first. What this stiffness is, what we are seeing here is what is the configuration of forces that is required to give me a rotation of 1 radian at my node B without any rotation or movement at node A and without any vertical movement of node B. This is a classical problem of indeterminate structural analysis which can be solved using any structural analysis method. I would prefer the moment area method to solve this, but this can be solved using slope deflection, conjugate beam, consistent deformation, or stiffness and flexibility approaches. Now, when we solve for this deformed shape, what we find out that we apply EI over L and B, and when we apply this moment to get 1 radian of rotation at node B, we have to apply a moment EI over L at node A. To prevent the frame element from rotating, we have to apply this force couple as at the supports of this frame element, and therefore this is the complete set of forces that will give me 1 radian of rotation at node B without causing any other degree of freedom at any other node. This 4EI over L is then the rotational stiffness of the frame element. And similarly, the next question that we ask is, what is the shear force that is required to cause a unit displacement at node B in the vertical direction? Again, we use independent structure analysis to calculate this force, and it turns out that this force is equal to 12 EI over L cube. From equilibrium, an equal and opposite force has to be applied at the other support, and to prevent the frame element from rotation, we have to apply equal and opposite moments at the two supports. So this 12 EI over L cube is then the shear flexural stiffness of the frame element. Um, Now let's look at a frame and consider two extreme scenarios that are sometimes possible. Um, Usually, our frame consists of beams and columns, both of which are flexurally flexible. And but occasionally, what tends to happen is we can have um, frame that has its beams that are infinitely rigid flexurally, and therefore when the frame is displaced towards in the right or left, the columns are bent in double curvature. So in this case, what tends to happen is my force that is being resisted by the bottom of these columns is then equal to 12 EI over h cube times u, and the same force is resisted by my left column, right? So if u is equal to 1, then that gives me 24 EI over h cube, which is therefore my lateral stiffness of the frame when all of my beams are of infinite stiffness. The other extreme that is possible is when my beams are very flimsy. Now, this is the scenario that is typically the case for when your columns are supporting your flat slab or flat plate. Now, for this case, your beam stiffness can be is approximately equal to 0, and when I displace my um, frame in the lateral direction, each one of the columns acts like a cantilever that is supporting a point load at its end. Now, we know that if P is my lateral force and L is my length of the cantilever, then the lateral deflection at the top of the cantilever is simply PL over 3EI, PL cube over 3EI. And so for a lateral displacement U, my force at the bottom of each of these columns is 3EI U over, this is a U, over H cube, and 3EI U over H cube. If my U is equal to 1, because I am interested in stiffness, then my lateral stiffness of the frame itself becomes 6EI over H cube. Note that for the case when my beam stiffnesses are approximately equal to 0, my lateral stiffness of the frame is 1/4 than it would have been when my beam stiffness is infinite. Next, let's consider another component of the mass trolley system, which is damping. So what is damping? Previously I had shown you a plot a couple of many slides ago, where we had a freely vibrating system without any damping, and the solution of the mathematical equation tells us that the system will continue to oscillate forever. Now, we know that this is never the case, because whenever a system is um, uh, disturbed from its equilibrium position and left to vibrate, it will oscillate about its equilibrium position a number of times, and it will eventually come to rest. And this is because there is a finite amount of wastage of energy every time any structural element or any system oscillates due to dynamic loading. Um, so, how do we then model this wastage of energy? We model this wastage of energy by introducing another term in our equations of motion, and another concept in our equations of motion is damping. Damping can be defined as um, idealization of wastage of energy due to different processes during each oscillation. Now, dampings are due to a number of different sources. In a lab specimen, in vacuum, whenever we oscillate a system and is not interacting with any other um, media or environment, most of the energy is lost due to thermal effect of straining of the material. Whenever we strain a material, there is a finite amount of thermal output as a result of it, and that is the energy that is wasted due to the straining of the element. And when structures are vibrating, all of the elements are straining, and there is wastage of this energy. So this first, you know, we one of the sources of damping is thermal effects of elastic straining. Next, in civil engineering structures and in mechanical engineering structures, when there are steel structures, they are connected to each other through bolting, riveting, etc. Nowadays, it's a more often than not it is bolting, and those steel elements, when they're connected to each other, there is a certain degree of friction that exists between the joint and the element, and that is also one of the reasons why steel structures lose energy during oscillation. For concrete structures, when we deform any concrete element, micro cracks open and close. The opening and closing of those micro cracks result in wastage of energy. One of the main reasons of wastage of energy of structures is due to the interaction of um, the structural components and the non-structural components. So, for example, we can have gypsum partition walls or any other non-structural component that does not deform by the same amount as much as the structural elements, but still they are interacting with the main structure, and they cause the vibrations to dampen down with the number of oscillations. Um, then for one of the main reasons of loss of energy during vibrations is air resistance. Whenever there is a structure or a building that is vibrating and oscillating, it is doing it in an air medium, and that is causing all sorts of drag and pressures to develop on both sides of the structure, and this is actually causing uh, loss of energy. For earthquake loading, one of the main reasons of loss of energy is the interaction between the structure and the soil medium, and this is actually nowadays one of the main areas of research in many universities around the world. Now, unlike stiffness, damping cannot be calculated using dimensions and geometry of the structural members, their connection configurations, and all that. And the reason is damping results from so many different processes, and each one of those processes is so difficult to objectively quantify mathematically. And therefore, the approach that is used in dynamics is to use equivalent damping to characterize the dynamic response of the structures. Um, Damping can, however, be measured. If we have a structure and we want to measure its damping, that can be done. And this is done by causing free vibration of the structure. And once that free vibration of the structure is, once the structure is freely vibrating, what we do is we measure the response of the structure at different times at its peak, and then we can correlate this and these two different the response of the structure at these two different peaks to get the damping of the structure. The difficulty with this approach is damping changes with the magnitude of lateral deformation or magnitude of loading of the structure. So even if we measure damping for a certain magnitude of lateral deformation, that amount of damping might not be applicable for another magnitude of deformation. So this we have the modeling approach, we have already discussed it. What we tend to do is we tend to have an equivalent damping value, and that equivalent damping value is equivalent of all of the energy losses due to all of the processes that are happening in the structure during oscillation to cause energy loss. Now, there are a couple of different types of damping that you should be aware of. We will be using viscous damping in our formulations, but and viscous damping means damping that is proportional to that is correlatable to the velocity of deformation in the structure. So, but there is another type of damping called Coulomb damping, and Coulomb damping is basically damping due to any frictional processes. We will not be considering Coulomb damping for the time being in our formulation. So whenever you see FD is equal to Cu dot, what this means is this is the damping force that is related to the velocity of deformation in the structure. U dot is the velocity of deformation in the structure by a coefficient called viscous damping, by a coefficient representing viscous damping. Um, so we've already discussed this above, viscous damping versus Coulomb damping. And for the time being, I think this is enough, and we will look at this subject more closely in later during our course. Now, let's consider our friend, the single story frame, subjected to earthquake loading. Now, strictly speaking, earthquake loading is not exactly the same. It doesn't appear to be exactly the same as application of a lateral force at the top of the single story frame. Um, and we will see that the two are actually equivalent to each other, but before we do that, we need to understand something that is only particularly relevant to earthquake loadings. And that is the frame of reference from which we are observing the lateral displacement of the frame element. So, since the ground is shaking itself, we assume that we have another stationary frame of reference that does not move with time. And relative to that stationary frame of reference, our ground is moving as a function of time by UG. Our frame is moving relative to the ground as a function of time again by this variable u. That means that the total lateral movement of our masses relative to this stationary frame of reference is equal to ug plus u itself. So, and this can be very easily seen here. If I extend this line here, then this is simply ug, which is my ground moving with relative to the stationary frame of reference, and this is u, which is the deflection of the frame relative to the ground. Now we need to keep this in mind when we consider our structures subjected to earthquake loading later during this lecture. Having been introduced to the different components of the single degree of freedom system, let us now address the problem of constitution of or formulation of equation of motion of a dynamically vibrating system. I will introduce you to three different philosophical approaches. These approaches would seem very similar to you for this trivial scenario that will be presented to constitute the equation of motion. But the fact is that you need to know all of the three different philosophical approaches, because under certain scenarios it will be very convenient to constitute the equation of dynamic equilibrium or constitute the equation of dynamic motion of a system using one approach rather than the other. So let us start with this first philosophical approach. And this first philosophical approach is based on a law that we have all learned in our high school. From Newton's second law of motion, we know that force is equal to mass times acceleration, which means that whenever a mass is subjected to a certain acceleration, it will require a certain amount of force for us to do that. Now, on my left is our single story frame, and on my right is shown the free body diagram of the mass itself. If I take account of all of the forces that are acting on my mass, I see that my mass is under application of force P, and this deformation is of the mass is resisted by my forces in the columns, which is my spring force Fs, and also the distortion in the frame is resisted by my damper, which is basically modeling of wastage of energy per unit oscillation or per during oscillations. Now, if I write all of this and take it to the left hand side of my equation, it results in this equation which has all the forces on the left side and mass times acceleration on the right hand side. Rearrangement of this equation gives me this equation, which is mu dot dot plus ft plus fs is equal to pt. Now I can further write this equation as mu dot dot plus cu, because dot, plus ku is equal to pt. Now ku dot is because ku is equal to, because my column stiffness multiplied by the lateral displacement will give me Fs, and Cu dot is basically because I'm using viscous damping, and my viscous damping is related to my velocity of distortion of the frame. Let's look at the second philosophical approach, which is basically called as dynamic equilibrium concept or the D'Alembert's principle. We have the same frame and we have the same mass as we had in the last slide. In this philosophical approach, we are not resorting to the Newton's second law of motion. Instead, what we are saying is that at any time instant t, our mass has to be in equilibrium under application of all forces, with one exception. What we are, what the D'Alembert principle tells us, or what the dynamic equilibrium approach tells us is, whenever there is a mass, there will be an inertial force, a fictitious inertial force that is acting in the opposite direction to the acceleration of the mass. So with this additional fictitious force, what we do is we resort to the equilibrium of all other forces at any time instant t in the direction of motion of the mass. And when we write that with this fictitious force, we get this equation, which basically is P minus Fd minus Fi minus Fs is equal to 0. Rearrangement of this equation gives us the equation at the bottom of my slide, and if I again use open up this equation, this gives me Ku Cu dot plus Mu dot dot. Again, this is basically because this is basically representing viscous damping, and this is representing my force in the columns due to lateral deformation. Okay. The third philosophical approach is to take our single degree of freedom system and to break it down into its different components, while realizing that the deformation in all of those components of the master system are equal to each other. So, for this system, let us consider the frame that we have been considering for the past two formulations. And our frame element is shown in figure A, and this is then broken down into three subcomponents. The first component is a simple frame element that is subjected to my force Fs. The second component is my damper system only, subjected to my damping force Fd. And the third component is my mass only, subjected to my inertial force Fi. Now, all of this mass, damper, and springs are subjected to the same lateral movement, identical lateral movement at all times, which means that my total force in the system, which is my system A, is equal to the force in system B plus C plus D. If I further elaborate this, this results in my applied force PT, which is the left hand side of the equation, is equal to my force in the springs, which is my system B, my force in the damper, which is my system C, and my force in inertial force, which is my system D. And if I plug in all of the forces and I carry the same expansions that I was doing for the previous two cases, I will end up with Pt is equal to mu dot dot plus fs plus fd, which is equal to mu dot dot plus ku plus cu dot, and this is the same equation that we had derived during using the previous two philosophical approaches. Next, consider a scenario where our single-story frame element is subjected to ground shaking and is not under application of any lateral force. Now, a few slides back, we had noticed that for this system, we need to establish a stationary frame of reference before we can write the equation of motion for this system. And so let's assume that this is the stationary reference, and if this is the case, then the total mass relative to this stationary reference is equal to the displacement on the ground plus the relative displacement of the mass to the ground. Now, writing using D'Alembert's principle and writing the equation of motion equilibrium in the horizontal direction for this case, we write sigma fx is equal to 0, and x being this direction, and this gives us the inertial force plus the damping force plus the stiffness force should add up to equal to 0. Now from D'Alembert's principle, my fictitious inertial force is equal to my inertial force is equal to my mass multiplied by the total displacement function of the mass relative to the stationary base. When I plug in the value of ut from this equation, what this gives me is mass times ug dot dot plus u dot dot. When I expand this, I get mass times u dot dot plus c times u dot plus k times u is equal to minus mass times ug dot dot. Now, all of the terms on the left hand side are written in terms of u, which is basically the relative displacement of the frame to the ground. And on the right hand side, we have mass times ugt, which is basically the product of mass m multiplied by the ground acceleration function. So this equation basically tells us that for a freely vibrating single story frame element, and in fact this can be generalized to any stories and any degree of freedoms and any dimensions, when it is subjected to ground acceleration, the lateral deformation and the response of the structure can be calculated by considering a stationary base with an effective force at the level of the mass in the lateral direction. So this is a very useful idealization because no longer do we have to rely on a stationary frame of reference to write the equations of equilibrium. Having established the equation of a motion of a dynamically vibrating system, we need to solve this equation of motion to get our response uh, prediction for the system. And so the differential equation that we have formulated is mu dot dot plus cu dot plus ku is equal to pt being the externally applied force as a function of time t. The classical solution, there are four different approaches to solve this equation of motion that we are going to talk about in this lecture. And the first approach is basically resort to the classical solution of this linear differential equation. The solution of this linear differential equation consists of a particular solution and a complementary solution. We can calculate, we can evaluate this using our mathematical approaches and get the value of u, which is the response of the structure as a function of time t. So this is what is you know one of the main methods to solve the linear differential equation. The second approach is basically based on the first approach, but the second approach is used to derive response of general loading of single degree of freedom structures. And what the second approach is basically we can take a general load, um, and we can break it into n number of um, impulse loadings, and this is I'm trying to draw n number of impulse loadings, any shape of impulse loading, triangular, square, or something, and then we can basically sum up the response of these n impulses and get the response of the structure subjected to this general loading. So Duhamel's integral, we're going to learn about this later during our course. Then the next sort of set of methods is the frequency domain methods. Again, basically what we do is we take the force function and we basically break this force function into its different constituents. So we can basically have this force function using Fourier transform or Laplace transform. We can have this as n sets of harmonic functions, and those n sets of harmonic functions are basically you know um, the response due to those is then used to get the total response. This is a very powerful tool, and we will definitely learn this how to do this later during our courses. The fourth type of method that we are considering is the numerical methods. Now, these methods are completely different from the first three type of methods, and they are the only category of methods that can be used to analyze non-linear response of uh, the structures subjected to dynamic loading. There are a lot of different types of these methods. For example, the constant acceleration method, then the central acceleration concept, etc. We will learn more about these methods again as we move during the course. Okay, so a bit of a roadmap as to how this course will proceed forward. First of all, we will learn about free vibrating systems where there is no external force applied on the system. So this will be step number one. After then that we will consider systems that are subjected to harmonic loadings. Harmonic means sinusoidal loadings, and basically periodic loadings. Periodic loadings are any loading that repeats after a certain time interval t, p. Now, these periodic loadings are basically they can harmonic loadings are periodic loadings, but periodic loadings might or might not be harmonic loadings. They can be any pattern of loading that repeats itself after a certain amount of time. Then we will learn about the impulse loading. This is where we learn about the Helmholtz integral and all that. And after that, we're going to learn how to calculate response of the structure subjected to random loading. This is where we're going to learn about the Fourier transforms and also the Duhamel's integral and all that. After we're done with the single degree of freedom systems, we are gonna go and we're gonna learn as to how to calculate the response of the multi-degree of freedom structures. Now, the multi-degree of freedom structure meaning structures that have more than one degree of freedom in two dimensions and structures in three dimensions. So I am gonna end my lecture here because I've spent more time than I had budgeted for this course during this week. And I will be solving a number of numerical problems during my next lecture because I think it is imperative that you guys, mm, you know, practice all of these concepts using at least 5 or 6 numericals before you can be comfortable with the concepts above. I encourage you to open the Chopra textbook and study the chapter number, I think this is chapter number 2. Um, Chapter number, number 1. And do let me know about if you have any issues. I'm gonna hold my Zoom office hours next Saturday, and yeah, I will be uploading a second part of this lecture containing numerical evaluations of different numericals. Please do go through this stuff and keep a minimum degree of focus on this course. Otherwise, you won't benefit from listening to all of